Hey everyone, and welcome. Today we are going to crack a classic coding puzzle. It's one of those problems that's just so satisfying to solve, and you see it pop up all the time because it's a great test of thinking efficiently. So let's just dive right in.
All right, so here's the setup. Imagine you're given this list of numbers: 0, 1, another 0, 3, and 12. Pretty simple, right? This is our starting line.
And this is our finish line. The goal is to get a list where all the non-zero numbers are pushed to the front. Notice they're still in their original order, 1, 3, 12, and all the zeros are shuffled to the back. But here's the kicker, the real twist. You have to do it all in place. That means you can't just create a new separate list. You've got to work with the one you were given.
Yeah, that one little rule, the in-place requirement, is what makes this a fantastic puzzle. It forces us to get a little bit clever and really think about how we're moving things around.
So let's just lay out the rules of the game super clearly. Rule number 1, get all the zeros to the end. Rule number 2, the other numbers, the non-zero ones, have to stay in the same order relative to each other. And rule number 3, the big one, you have to do all of this by modifying the original list directly. No copies allowed.
So how do we tackle this? Well, with a really elegant technique, that's how. We're going to use a super common and powerful approach called the two-pointers method.
The idea behind two-pointers is actually pretty straightforward. You just use two markers to keep track of two different spots in your list at the same time. And this simple trick lets you solve a ton of problems, just like this one, in a really efficient way, usually by going through the list just once.
To make this really easy to picture, let's give our two pointers some jobs, some personalities. We'll call our first pointer I, the scanner. Its job is to just scan through the list, element by element, from the start all the way to the end. Simple. Our second pointer, K, we'll call the writer. The writer is a little more picky. Its job is to mark the next open slot where a non-zero number belongs. It doesn't move an inch until it actually writes something down.
Okay, that's the theory, but it's way more fun to see it in action, right? So let's walk through our example and watch how the scanner and the writer work together to get the job done.
So we start out at the very beginning. Both our scanner, I, and our writer, K, are pointing at the first element, index 0. The scanner looks down and sees a 0. Well, since the whole point is to move non-zero stuff, the writer has nothing to do here. It just waits. So the scanner moves on to the next spot.
Okay, now the scanner I is at index 1, but notice the writer K is still back at index 0 waiting for something good, and boom! The scanner finds the number 1. It's a non-zero number. This is exactly what the writer's been waiting for. It's time to make a move.
So, we swap them. The one from the scanner's position gets swapped with the 0 at the writer's position. Our list is already looking better, and since the writer just did its job, it gets to move up one spot to index 1, ready for the next assignment.
On we go. The scanner moves to index 2, while the writer is holding strong at index 1. The scanner finds another 0. So what happens? You guessed it. Nothing. The writer stays put, and the scanner just keeps on scanning.
Now the scanner, I, hits index 3 and finds the number 3. Bingo! Another non-zero number. Our writer, K, is still patiently waiting over at index 1. So it's time for another swap. We'll swap the 3 with the 0 that's sitting in the writer spot.
And look at that! The array is really starting to take shape. The non-zero numbers are clumping together at the front, and they're in the right order. The writer did its job at index 1, so it gets to move up to index 2. All right, last one. The scanner I lands on the final element, which is 12, at index 4. Our writer K is at index 2. So we do our final swap. The 12 gets put into the writer slot. And that's it. The scanner has reached the end of the list. And our final result is exactly what we wanted. 1, 3, 12, 0, 0. All the non-zero numbers are at the front, in order, and the zeros are at the back. Puzzle solved. Beautiful. So now that we've walked through the whole idea, let's see how this logic translates into actual code. You'll be surprised how clean and simple it is. You can literally see our little story playing out in the code. We start with K equals 0. That's our writer getting ready at the starting line. The for loop is our scanner, I, marching through the list. The if X is the scanner checking, hey, is this number something other than 0? If it is, we do that nifty Python swap. That's the action we saw. And then K plus 1. That's our writer taking one step forward after a job well done. It's a perfect one-to-one match. So why is this two-pointer trick so great? Why is it considered such a good solution? Well, it all boils down to being incredibly efficient.
Here's the magic. We only had to look at each element in the list one time.
The scanner just moved from left to right and never had to go back. That's what we call a single-pass algorithm, and it's a huge sign of an efficient solution. If we get just a little technical, we can see how good it is. The time complexity is O of n, which is just a fancy way of saying the work grows in a straight line with the size of the list. Double the list, double the time. Super predictable. And the space complexity is O of 1, which means we used a constant, tiny amount of extra memory. In other words, we kept our promise. We didn't make a copy, we solved it in place.
So now you have this powerful idea in your toolkit, this concept of a scanner and a writer partitioning an array in one clean pass. I'll leave you with a question to think about. What other kinds of array puzzles, maybe with sorting or finding pairs, could you solve using this same elegant technique?